All right, so now we're going to move on to our first elimination reaction mechanism, the E2. So much like, well, so first of all, let's remember what the elimination reaction is. That's when we have a alkyl halide and a base, and the hydrogen on the beta carbon gets removed along with that halogen on our alpha carbon in order to form that double bond, right? So you get an alkene at the end of the day. Okay. So what is E2? Much like SN2, it is a concerted reaction mechanism, meaning that the base reaches over to grab that proton at the same time that that pair of electrons comes down to form a double bond and loss of the leaving group. So what's an E2 reaction is that all of this happens at the exact same time. This is another concerted type mechanism. And I guess just to make sure we can follow along here, right, the first step would be proton transfer. We have loss of a leaving group. Importantly, what's happening here, notice that that pair of electrons that used to be in that carbon-hydrogen bond, but now that proton's being lost, right? So that pair of electrons is still there on that carbon. This is going to be the formation of that pi bond, is what this particular arrow represents. Okay, but again, E2 is the fact that it's a concerted mechanism, meaning that you're losing the proton, that double bond is forming, and the leaving group is being lost all in the same step. We'll see that E2 reactions happen because you have a strong base. And again, where does the 2 come from? Where does the 2 come from? It's because it's bimolecular, right? So it's one step, but it's the fact that both the alkyl halide and the base play a role in that step. Both of those molecules together are determining that rate limiting step. So really, again, the 2's always refer to what happens in terms of the rate constant. And so you have the alkyl halide and the base that are playing a role in determining the rate of that reaction. This is where I sort of broke from the book a little bit. The book, this chapter is really long as it is. The book itself goes into alkene nomenclature and just a lot of detail about alkenes. Chapter 8 is when we start focusing on reactions of alkenes. So I felt that that was a more appropriate place to deal with alkene nomenclature. But there are 2 main things that we need to know about alkene stability in order to be able to correctly predict the products of an elimination reaction, okay? So first of all is the difference between cis and trans, or, remember we have that EZ nomenclature as well. Which of these is going to be more stable? So generally speaking, the cis conformation, or the conformation where big bulky groups are on the same side, are going to be less stable, right? Because when you put big bulky groups on the same side of that double bond, you get steric strain out of it. This model picture of this molecule might look a little weird. These are what we call space fill models, where we try to imagine the actual size of a carbon and a hydrogen given its electron cloud size. You can see that the size of the electron clouds are quite big compared to what we draw when we do our bond line structures. But anyway, it illustrates nicely the fact that when you have these 2 methyl groups on the same side, they have steric strain. So then you can imagine replacing them with something even bigger and bulkier, and that just makes it even less favorable. The trans conformation, where they're on opposite sides, are considered to be more stable. Okay, so in terms of thermodynamics of forming an alkene, generally speaking, the trans alkene is going to be more stable than the cis alkene. Okay, and now in terms of substitution on alkenes. So these are how many different groups you have on either side of the bond. A monosubstituted, meaning that the alkene has only one allylic carbon are going to be considered the least stable. If you have two of them, of course you want them on opposite sides to be the most stable, but even, or to be trans, but even then, di-substituted would be less stable than tri-substituted, less stable than tetra-substituted. Okay, so the bottom line is the more alkyl groups you have on that alkene, the more stable that alkene is. Okay, so sort of very simple, but again, we're going to need to predict what products happen in an elimination reaction. First of all, bulky groups want to be on opposite sides. They want to be as far away as possible. But another factor, probably a little bit more surprising factor, is the more highly substituted that alkene is, the better. And again, this actually goes back to this, I call it the weird, mysterious phenomena of hyperconjugation, right? Where you have bonding orbitals interacting with anti-bonding orbitals and stabilizing. Okay, so how do we figure out what the products are of our elimination reaction, right? So first of all, the first step you got to do is figure out what your beta carbons are, because remember, the hydrogen has to be lost from the beta carbon. If both of your beta carbons don't have hydrogens, there can't be an elimination reaction, right? So in this case, we have these two beta carbons, those are kind of identical. And then we also have this one here, right? So hydrogens can be lost from any one of these in order to form the elimination product. So in this case, there would be two different ones. Again, both of those green carbons would be like, give you equivalent products if you had an elimination there. First one would be if the blue beta carbon lost its hydrogen, and the second would be if one of those green beta carbons lost its hydrogen. But now, given what we just learned on the last slide, which of these two alkenes is considered to be the more stable alkene? Right, so more highly substituted is better than only having two substitutions, right? So you have 2 versus 3. So in this case, this would be the dominant product, right? Your more stable alkene, because it's more highly substituted. This is what's called the Zaitsev product versus the Hoffman product. So the more highly substituted product is the Zaitsev, the less highly substituted is the Hoffman. Clearly named after two dudes. I don't know, but yeah. Just another way to refer to it. Again, more highly substituted, more stable. Okay, so this has this sort of selectivity has a fancy word to it, which is regioselectivity. Okay, regioselective is when different constitutional isomers can be formed. Note that these two products are different constitutional isomers. Same molecular formula, but their connectivity is different. Okay, so this is what we would call a regioselective reaction, is when you have two different constitutional isomers that can be formed, and you have to consider which one would be formed in that particular case. In this case, specifically given this base, we're going to see that the more stable alkene will be formed, the more highly substituted. You can actually choose, sort of tune this to maybe produce more of the Hoffman product or more of the less highly substituted through your choice of base. So let's see how that would happen. So again, we saw with this what's called an ethoxide ion, that we would have this like 70-30 distribution, okay? But what about if we, and again, that's because we're talking about removing hydrogens from, there's actually these two equivalent carbons, but let's just consider these two. And again, this would be if I had lost from that green carbon, and this would be if I had lost from that blue carbon. But now what if we use what's called tert butoxide. So first of all, structurally, what's the difference here is we have a bulky base or a sterically hindered base with all those different all those different substitutions on that carbon group. That's going to affect this base's ability to approach what is the more sterically hindered hydrogen. In this case, that blue hydrogen is more sterically hindered than the green, than the green set of hydrogens, because the green set is on a methyl group, so it's sticking out on the end, whereas the blue is on that CH2, right? So this is going to, by using a bulky base, we can change the distribution to instead favor that Hofmann product. Again, all having to do with sterics. Sterics is going to be really important in this chapter. Because the base is bulky, it's unable to approach the more sterically hindered carbon. And then we can take this to like the umpteenth level by using an incredibly sterically hindered base or an incredibly bulky base. And that will change our distribution even more in favor of that Hofmann product, right? So when you're just using any regular old base, so for example, the ethoxide, or an even smaller one would be the hydroxide ion. So hydroxide would probably even change it even further in terms of, we'll call this like 90-10, right? Because it's really small, so it has no problem accessing that sterically hindered carbon. Well, then your main consideration is just which alkene is more stable. Once you start having a bulky base, now all of a sudden you have to factor in that bulkiness in terms of which one of those hydrogens is going to be the more accessible one. Some bulky bases that we're going to see over and over again. So tert butoxide is going to be really key. You might see this also without the potassium. Remember when I told you see a potassium or a nitrogen or a sodium, you want to think negative charge. Diisopropylamine or triethylamine, these are also bulky bases. Even more famous are DBU and DBN. These are, let me just draw it real quick. There's a nitrogen there. These are, again, just really bulky bases. DBU is the same thing, but instead of having this 5-membered ring here, it's a 7-membered ring, which I'm particularly terrible at drawing, so I don't want to attempt it. Bottom line is these are just examples of bulky bases, okay? Sterically hindered bases, again, you'll hear me call them bulky bases. What really the big thing about bulky bases is they're also terrible at being nucleophiles. So these are examples of strong bases that are bad nucleophiles. Usually basicity and nucleophilicity are kind of one and the same thing. A good nucleophile is a good base. When you have a bulky base, they're great at being a base, but not so good at being a nucleophile. Okay, so then let's just go through a few examples here. What do we have to consider? So again, when we have a hydroxide, that's a strong base, but it's nice and tiny. So we would expect instead, looking at our different possible beta carbons, we would expect to just get the more highly substituted, or that Zaitsev product. So in this case, we would expect something like this. We can have a minor amount of the non-Zaitsev product. But this would be our major. All right, and again, just because it's more substituted. Notice how what I was doing right there to make sure that I got the exact right structure is counting carbons. Counting carbons is the best way to make sure that you haven't made an error. So if I'm ever like, oh, did I draw enough lines? I'll go through and dot, 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 dot. That's me counting carbons really quick. All right, but now we're going to use a big, so I have these same 3 beta carbons to consider, but now I have tert butoxide, that big bulky base. So now my 2 products are going to be the same. But here, the Hoffman or the non-Zaitsev is going to be the major product. This is really messy. All right, and then this last one, I have an ethoxide ion that's going to be playing the role of my base. 2 beta carbons to consider. Oh, -3. 3 beta carbons to consider. I feel like a lot of people are going to be tempted to immediately go for that more highly substituted one, right? Where the double bond is formed here. What's the problem with this product? This carbon has 5 bonds. It's just not going to happen. So we should be able to spot that this will never occur because this beta carbon right here doesn't have any hydrogens to participate in, to be eliminated. So first step you got to do, on top of all these other considerations, I know it's a lot, but the first thing you got to do is figure out which carbons actually have beta hydrogens. So this wouldn't be produced at all. It just doesn't exist. So then I have these 2 other products to consider. And in this case, because I don't have a bulky base, I have a normal base, my major product will be the one that forms the more highly substituted alkene.